In this lesson, we're going to look at probability. We're going to look at a couple of ways of calculating probability, namely theoretical probability and experimental probability. We're going to look at a rule when we want to work out the probability of something or something, and another rule for when we want to work out the probability of something and something. We're going to consider events which are dependent on each other. We're going to see how we can represent probabilities in a diagram called a tree diagram, and finally we're going to look at a formula called Bayes Theorem. So what is probability? Well, probability tells us how likely something is to happen, and it's usually measured on a scale from 0 to 1. 0 means it definitely won't happen, and 1 means it definitely will happen. And it's usually written as a fraction or a decimal. So if, for example, we thought the chance of something happening was 50-50, we say it has a probability of 0.5 or half. And the closer to 1, the more likely it will happen. So let's say, for example, you thought the probability that you will find this lesson exciting is about 0.4, it would go there on this scale. And then let's imagine you thought the probability of you passing the module was, say, about 0.75, then it would be roughly about there on the scale. Note that sometimes probabilities are also written as a percentage, so a value somewhere between 0 and 100. Let's have a look at a method for calculating a probability. We can use the formula: the probability of a success equals the number of possible successes divided by the number of possible outcomes. And this assumes that all the outcomes are equally likely. So for example, say we were asked to calculate the probability of getting an even number on a dice. Now we know on a dice there are the numbers 1 or 2 or 3 or 4 or 5 or 6. We're interested in getting an even number, so that's our success in this case, an even number. So the possible even numbers are 2, 4 and 6. So using our formula, the number of successes is 3, the number of outcomes is 6, so the probability of getting an even number on a dice is 3 over 6, which cancels down to half. Now that formula only worked if the outcomes were equally likely. So sometimes we don't know all the outcomes are equally likely, so sometimes we may need to conduct an experiment or collect some data to determine a probability. If we do that, then the formula changes slightly. It becomes probability of success equals number of successes divided by number of trials. So let's imagine you wanted to find out the probability that a particular diet drug helps people lose more than 1 kilograms in weight. So you give the drug to 25 people and record their change in weight. And you find this. You find that 3 people lose more than 2 kilograms, 8 people lose 1 to 2 kilograms, and so on. So we wanted a probability that a person loses more than 1 kilogram. So using our formula, the number of trials is simply the number of people. So there are 25 people in this case. The number of successes is the number of those that lost more than 1 kilogram. So we can see from our table, 8 lost 1 to 2 kilograms, 3 lost 2 kilograms or more, so in total 11 people lost more than 1 kilogram. So therefore our number of successes is 11. So the probability is 11/25. Now let's have a look at how to calculate the probability of something not happening. Let's imagine there's a 70% chance of it raining tomorrow. Then clearly the chance it doesn't rain is going to be 30%, or 0.3. So in general we can deduce from that that the probability of something not happening is 1 minus the probability that it happens. So for example, if the probability that a person catches a particular disease is 0.2, we can find the probability they don't catch the disease by simply doing 1 minus 0.2, which is 0.8. Now let's look at the OR rule. This tells us that the probability of A or B happening is the probability of A plus the probability of B. So let's have a look at an example. In a room of 14 people, 5 have black hair, 6 have brown hair, and 3 have blonde hair. What is the probability that someone picked from the room at random has black or brown hair? So using our formula, the probability of black or brown equals the probability of black plus the probability of brown. The probability of black is going to be 5/14 because there are 14 people altogether, 5 have black hair, so it's 5/14. The probability of someone having brown hair is 6/14. So we add them together, which gives us 11/14. Please note that this rule only applies if A and B can't happen at the same time. Now the posh term for that is mutually exclusive. So in this example, we can apply the rule. They are mutually exclusive because nobody has black hair and brown hair. Let's however consider this example. Let's imagine in a room of 16 people, 7 of them are male, 9 of them are female, and 8 of them are aged under 25. Now if we wanted to find the probability that someone is female or aged under 25, we can't simply use our rule, our OR rule. We can't just add them together because somebody could be both female and under 25. So in this case, we would need some extra information if we wanted to calculate our answer. Now let's have a look at the AND rule. If we have two separate events, then the probability of A and B both happening is the probability of A multiplied by the probability of B. For example, you throw a dice and a coin. What is the probability of getting a 6 on the dice and heads on the coin? Using our rule, the probability of getting 6 and heads is the probability of getting a 6 multiplied by probability of getting heads. So it's going to be 1/6 times a half, which is 1/12. Note that this formula only applies if A and B are independent. Independent means whether or not A happens doesn't affect whether B happens. So here they are independent, because whatever score the dice gets, that's not going to affect the score on the coin. We might sometimes need to combine the AND rule and the OR rule. Let's look at this example. The probability that a student passes his maths exam is 0.7 and that he passes his English exam is 0.8. What is the probability that he passes exactly one of those exams? So if we want the probability that he passes exactly one exam, that means either he passes his maths and doesn't pass English, or he doesn't pass maths and he does pass English. So if we substitute the values in, the probability he passes maths is 0.7. The probability he doesn't pass English is 1 minus 0.8, which is 0.2. So if we want both those things to happen, we have to multiply 0.7 by the 0.2. Now we have an or here, so we have to add, and the probability he doesn't pass maths is 1 minus 0.7, which is 0.3, and means we multiply, and pass English 0.8 goes there. So calculating this, we end up with 0.38. Have a go at this practice question. The probability that it rains tomorrow in London is 0.4 and in Beijing is 0.2. What is the probability that it rains tomorrow in exactly one of those places? The probability it rains in one of the places means we want the probability it rains in London and it doesn't rain in Beijing, or it doesn't rain in London and it does rain in Beijing. So we get 0.4 times 0.8 plus 0.6 times 0.2, which gives us 0.44. Now let's have a look at dependent events. Now, if the second event is affected by what happens in the first event, then we say the two events are dependent. So for example, in a room of 14 people, 5 have black hair, 6 have brown hair, and 3 have blonde hair. 2 of them are taken from the room. What is the probability that they both have black hair? So we want the probability they both have black hair. So it's the probability the first person's hair is black and the second person's hair is black. But we can't use our AND formula from earlier. We can't do that. 5/14 times 5/14. That's because the two events are dependent. Once the first person has left the room, the probability that the second person has black hair has changed. Really, the calculation should be this, because the probability that the first person has black hair is going to be 5/14. But once that person has left the room, there are only 13 people left in the room, and only 4 of them have black hair. So the probability that the second person has black hair is only going to be 4/13. So we need to multiply these two numbers together. So how we'd say that is the probability the first person has black hair, which is this, multiplied by the probability that the second person has black hair, given that the first person has black hair. So what this means is, if our two events A and B are independent, our formula from earlier needs to change slightly, and it now becomes this. The probability of A and B equals the probability of A multiplied by the probability of B given A. So let's have a look at an example. In a particular town, the probability that someone catches a particular virus is 0.2. If they have the virus, the probability that they show symptoms is 0.6. What is the probability that someone catches the virus and shows symptoms? So we want to calculate the probability they catch the virus multiplied by the probability they show symptoms given that they've caught the virus. So it's 0.2 times 0.6. So effectively we do still multiply the probabilities together, just like we did on the original formula. It's just that the notation has changed. Now let's look at tree diagrams. We can use tree diagrams to illustrate multiple events. Let's have a look at this example. 1% of people suffer from a particular disease. A test for this disease has been developed. If you have the disease, then the probability that the test correctly diagnoses you as positive is 0.7. However, if you don't have the disease, then the probability that the test correctly diagnoses you as negative is 0.6. So showing this on a tree diagram. You either have the disease or you don't have the disease. So this is shown by these two branches here. And we know that 1% of people have a disease, so we can put a probability of 0.1 here. And therefore we know the probability they don't have the disease is 1 minus 0.01, which is 0.99. Now, if they have the disease and they go and take the test either comes out positive or it comes out negative. We're told in the question that if they have the disease, the probability the test correctly diagnoses you as positive is 0.97. So 0.97 goes here. And so therefore, the probability that it doesn't correctly diagnose you is going to be 1 minus that, which is 0.03. Then we're also told in the question, if you don't have the disease, the probability that the test correctly diagnoses you as negative is 0.96. So that goes here. And therefore, the probability that if you don't have the disease and the test shows you as positive is going to be 1 minus that, which gives us 0.04. Now we can use our tree diagram to calculate various probabilities. So first, let's imagine we are asked to calculate the probability that a person has the disease and tests positive. All we need to do is move along the branches to the corresponding places. So the question says, has the disease and test positive? So we need to go, has the disease, test positive. We multiply these two values together. So the answer is 0.0097. Now part B says test positive. Now if someone's going to test positive, they could either have the disease and test positive, or they could not have the disease and test positive. So we need to consider this or this, so we need to add them together. So our answer is 0.0493. Finally, the question says, what is the probability that a person tests negative? So if they test negative, they're going to either have the disease and test negative, or not have the disease and test negative. Adding those together, we get 0.9507. have a go at this practice question. The probability it's sunny tomorrow is 0.6. If it's sunny, then the probability that Angela will feel happy is 0.9. If it isn't sunny, then the probability that Angela will feel happy is 0.7. That's the scenario. Have a go at answering these questions. So your tree diagram should look like that. The probability it will be sunny tomorrow and Angela will feel happy is 0.54. The probability it won't be sunny tomorrow and Angela won't feel happy, we move along these branches. So we get 0.12. And the probability that Angela will feel happy, we need to consider that scenario and that one, add them together, so we get 0.82. Finally, we're going to look at a formula called Bayes Theorem. Now we had a formula earlier. If events A and B are dependent, then the probability of A and B equals the probability of A multiplied by the probability of B given A. If we rearrange this, we get the probability of B given A equals the probability of A and B divided by the probability of A. This is called Bayes' theorem. And we can use this to find the probability of B given A. Let's have a look at an example. In a class, there are 10 males and 12 females. 4 of the females wear glasses and 6 of the males wear glasses. What is the probability that someone wears glasses given that they are female? So we could use Bayes' theorem to calculate this. Whenever we see the word given, that means we can use this formula here. And then part B, a similar question, what is the probability that someone is female given that they wear glasses? So the probability of glasses given female is a probability of female and glasses over a probability of female. Now the number of people who are female and wear glasses is 4. So the probability of someone in that group, in that class, being female and wearing glasses is 4 over 22, because there are 22 people altogether. So we get 4 over 22. And the bottom of the calculation is probability of female. There are 12 females, 22 people altogether, so the probability of female is 12 over 22. So doing our calculation, we end up with 1/3. Probability that someone is female given that they wear glasses. Again, we use our formula here. So it's going to be the probability they wear glasses and female divided by the probability they wear glasses. Now actually, the probability they wear glasses and are female is exactly the same thing as the probability they're female and wear glasses. So we worked that out earlier, that was 4/22. So the top part is 4 over 22, the bottom part is the probability they wear glasses, and we can see that 4 females and 6 males, so 10 people wear glasses altogether out of 22, so that's the probability that someone in their class wears glasses, 10 over 22. We divide them and we get 2/5. Let's have a look at another Bayes' theorem example. 1% of people suffer from a particular disease. A test for this disease has been developed. If you have the disease, then the probability that the test correctly diagnoses you as positive is 0.7. If you don't have the disease, then the probability that the test correctly diagnoses you as negative is 0.96. So actually this is the same example that we've looked at earlier in the lesson. This time we are asked to find the probability you have the disease given that you test positive, and also the probability that you have the disease given that you test negative. So it might help to represent it on a tree diagram. You don't have to, but often it helps. So this is our tree diagram from earlier. And if you remember, we can obtain all these probabilities by simply multiplying along the branches. So part A asks us to calculate the probability they have the disease given that they have tested positive. So using our formula, our Bayes theorem, it's the probability they test positive and they have the disease divided by the probability they test positive. So test positive and they have the disease is the same as have disease and test positive. So it's moving along these branches. So it's this 0.097. So the top part is 0.097. The bottom part, probability they test positive, it's basically have disease and test positive, or don't have disease and test positive. So it's this one plus this one. And that gives us 0.197. Part B, the probability they have the disease given that the test is negative. Again, we use Bayes' theorem, which means it's the probability they test negative and have the disease divided by probability of test negative. So probability test negative and have disease is the same as have disease and test negative. So it's this value here. Then the probability they test negative is basically this one plus this one. Which gives us that. So our answer is 0.0031. So a reminder, we've looked at a formula for calculating theoretical probability, which was the number of possible successes over the number of possible outcomes. We looked at a formula for experimental probability, which was the number of successes divided by the number of trials. The OR rule tells us the probability of A or B is the probability of A plus the probability of B. The AND rule tells us the probability of A and B is the probability of A multiplied by the probability of B. A dependent event is one which changes depending on what's happened before it. We can show probabilities on a tree diagram, and Bayes' theorem is a formula for calculating the probability of something happening given something else has happened.